This is a partial recording of the 2025 NeurIPS tutorial, The Science of Benchmarking, What's Measured, What's Missed, and What's Next. I'm Saxon, a postdoc at the University of Washington. All right, let's get started. So my part of this presentation is the second one, What's Missed. What do we mean when we ask, what's missed? There are many criticisms of modern benchmarking practice, which are easy to miss when we design a new one. Here we're going to borrow from a few works at a high level in order to introduce problems in benchmarking which have been previously discussed. These include Can We Trust AI Benchmarks by Eriksson et al., my own work, Benchmarks as Microscopes, from column 2024, and Raji et al.'s work, AI and the Everything in the Whole Wide World Benchmark. Many fundamental challenges and critiques have been levied, but are often missed by practitioners. The four big categories of missed considerations that we consider are data issues, measurement issues, systemic issues, and epistemic issues. We'll discuss both the critiques themselves and some solutions that have been presented and others may want to apply. Central to many of these critiques are validity issues. These can be divided into two classes: internal validity issues and external validity issues. Internal validity issues in a work arise from a single benchmark or resource not being made well or not fitting to some task. However, external validity issues also exist, where the world itself of the task is ill-defined. Construct validity might be the most important property of a good evaluation resource that is often missed. From Raji et al. 2021, the definition of construct validity is how well does a resource measure what it purports to measure. Unfortunately, this is more of an abstract goal than a concrete requirement for some resource, and many of the issues with benchmarks can be traced back to a lack of construct validity. Okay, so let's introduce data issues. Data issues are challenges to the validity of benchmarks, which arise when the benchmark is created. These include life cycle problems, questions of where and when the data is created, noise and spurious correlations, where bad examples harm the ability of the benchmark to discriminate between good and bad models. These issues can also be driven by positionality of the resource creator, which leads to poor construct validity, as well as contamination, where samples from the benchmark end up getting trained on by models. A key distinction for understanding life cycle issues in benchmarking is that between static and dynamic resources. Most dominant benchmarks are over static sets of exemplars which get collected once and held as a test set forever. Static dataset life cycles end, in a way, when the benchmark is released. However, reality is dynamic. A dynamic benchmark would be evolving and changing as the world changes. Static multiple-choice question datasets, according to McIntosh et al., fail to reflect the evolving nature of human-AI interactions. Static datasets have no way to account for future improvements in model capabilities. So why do we get stuck with these crappy static benchmarks? Well, first off are there life cycle challenges in creation. Producing high-quality data is costly and time-consuming. Consequently, we often rely on reduced, reused, and recycled data, a critique from Koch et al. In their study, they found that 70% of computer vision datasets reuse data from other domains. For example, in this pie chart on the right, they show that the original data source for image generation datasets, when divided out by task, only has 7.4% of them being built for the actual purpose of image detection, and datasets for other purposes like object recognition, face detection, or scene understanding get leaked in. This can cause a variety of problems, including that whatever errors are present in the downstream datasets propagate upstream. There are many egregious examples of bad data that have survived even in these huge datasets over time. For example, on the right here we have an example from MS Coco, where a picture of a train filled with trucks and people standing on top of it has a tiny segmentation annotation in that bottom right corner of a car, and no segments for the objects that take up the dominant portion of the frame. There are even worse examples, like here, a mask produced by an annotator in this picture of many, many people in a scene. As you can see, they clearly got so frustrated masking out all the people in the scene that in anger they drew out a 4-letter word as part of the mask. This example then lived on forever as MS Coco got used for more and more different tasks. So these bad labels are present all over. Who cares? Well, first of all, these present artifacts, which could cause systemic spurious correlations that models use to cheat on tasks. Some examples include Oakden Rayner et al.'s documentation of how in medical scan classification, the models would just look at secondary signifiers like what hospital an image was taken in rather than the existence of the case or not, or an entailment recognition, where models, when they're asked to tell if two sentences entail or contradict each other, they instead attend to surface semantics in the conclusion sentence, as there are systemic biases in the way that annotators write those sentences. However, more troublingly, bad labels produce noise, where an LM's performance is effectively random over examples that have incorrect answers. What does label noise cause? Well, here's one example. Vendro et al. Removed all bad examples from the math dataset GSM-8K. After removing the noise ceiling, making 100% accuracy possible, the ranking swapped. So what this chart here shows is in the blue the scores by a series of models on the original GSM-8K, which contains around 50 examples that have bad labels. In other words, the incorrect answer is marked as correct. What happens when you ask a model to answer those questions is that if it randomly guesses the correct answer, or if it gets the answer wrong, it will actually be scored as correct. And once those examples are removed, in the gold numbers here, we see that the ranking flips completely. The best performing model, Claude 3.7 Sonnet, becomes the 6th or 7th worst performing. Noise doesn't just introduce a ceiling on the highest performance a model can get. It also sets the overall resolution. So how do we deal with this? Well, one way you can remove noise in benchmarks is fluid benchmarking. This is a work from this year's column, which draws on item response theory. What item response theory does is it models capability of a test taker as a latent property that gets inferred not just from the number of correct answers they provide, but from the difficulty level of questions that the test taker is able to reliably answer correctly. To do this, each question under an IRT model gets fit a difficulty and discriminability. So in their column work, Hoffman et al. Trained an IRT model on some benchmarks, and by using the IRT model to select the next test question that a model gets given, they can iteratively update the capability estimate of it. And what this does is it naturally removes the noise samples because these have low discriminability, and it selects the answers the model is most likely to not perform randomly on. In effect, this turns a noisy dataset into one with higher resolution, as shown in this plot on the right, where they convert a dataset from being effectively useless to track training progress into one that has a monotonic increase as the model gets trained. Another oft overlooked problem in data gathering is annotator positionality. Many tasks that we want to evaluate are inherently subjective. Some examples include generative humor, assessment of hate speech, and more generally, text generation safety. Some tasks might not be objectively subjective, but have subjective attributes at many times. Examples include the acceptability of generated phrases, in other words, the question of whether some sentence is grammatical. Not all native speakers are going to agree on the grammaticality of all phrases. Another example is, once again, entailment detection, or NLI. Annotators may disagree on how well two sentences fit together in entailment. Typically, the way we deal with this subjectivity is to average or majority vote between generated examples. But is this ideal? Well, one study that tests this was Dung et al., where they introduced annotator embeddings to try to handle this inherent disagreement across humor detection, hate speech, and NLI tasks. What they did was to keep the disparate annotations, they instead framed the learning task as predicting the label of an input alongside a latent descriptor of the annotator. With these annotation embeddings, they were able to actually successfully identify the principal components driving subjectivity on these tasks and boost the classification performance over using the text alone, on some examples like sentiment analysis, by a very large gulf. Another problematic positionality issue is disagreement over definitions of things like tasks. For example, how dataset developers understand a task is another core component of positionality. From Subramanian et al., they looked at how the same task, in scare quotes here, can often be operationalized differently between different papers. Usually, these tasks are also poorly defined. They find a direct relationship between how well defined and consistently defined the task is and the overall dataset quality. In other words, poor conceptualization of a task leads to poor data collection. Another type of positionality are the values inherently embedded in the source of data. Many LM datasets get their test questions from web forums such as Reddit. Examples include HelloSwag and the ethics dataset. These in turn get recycled into bigger resources like MMLU, following that reduced, reused, recycled paradigm we discussed before. One example of a dataset that often gets used, a data source that often gets used, is the subreddit Am I the Asshole? Am I the Asshole dilemmas often cover basic interpersonal dramas, like disagreements between extended family members or friends. Are these really the bounds by which ethics in AI systems should be assessed? Finally, there are culturally contingent values which drive annotator positionality. For example, conceptualization itself is culturally embedded. What counts as a stereotype or offensive language, for example, are inherently culturally contingent and contested. Even annotations themselves can be culturally contingent, as described in my work with O et al. 2025. This is illustrated humorously in this chart, where the meanings of different terms and annotators can mean different things. In particular, Californian going from awesome meaning bad to awesome meaning great, versus the British interesting distinction. For example, in one study, East Asian annotators consistently preferred lower valence answers on a Likert scale to Americans. In other words, the Japanese and Chinese annotators were more likely to give mid responses, whereas Americans were more likely to give extremely positive or extremely negative answers. These influences will fundamentally shape the curation of datasets, which in turn get used to test models. A final sort of data positionality that's important to consider are the community values that get embedded in our resources. Benchmarks are normative instruments in the community. Investment in them helps drive the priorities of developers. For example, the significant investment made in safety benchmarks by effective altruist types have successfully driven others to work on alignment and safety. When we look to build systems that can do everything and want to evaluate their ability to do everything, we need to keep in mind that we're not experts in most things. Many domain-specific resources that get produced by computer scientists are found to not be useful for experts in those domains. For example, Blagett et al. Surveyed medical practitioners about how well clinical LM benchmarks meet their needs, and it's probably not surprising that those resources fail. Benchmarks are often abstracting tasks out of their social context. And finally, the work required to produce data is often undervalued relative to model work, in turn leading for lower quality resources to get out there. The final data issue we're going to consider here is contamination. Contamination is when samples from a benchmark get leaked into the training data for models that are tested on the benchmark. This fundamentally challenges the utility of an evaluation. It leads to poor predictiveness of the model on some end task and lower construct validity. For example, GPT-4 probably exhibited leakage of Codeforce's test tasks. On the easiest problems on Codeforces, it was able to get 10 out of 10 pre-2021 answers. However, it was able to solve 0 out of 10 recent problems. So how can we address contamination in data? One proposed method is the How Contaminated is Your Benchmark paper from Choi et al. They introduced kernel divergence scores as a proposed white box technique to test for contamination. What this entails is checking how much the RBF kernel of some embeddings diverges, given some test documents before and after fine-tuning the model on them. The idea here is that the representations of documents that have been seen already during pre-training are not going to change very much when they're fine-tuned on. However, the documents that were not present in training are going to lead to much larger updates in the weight space and thus a difference in the embeddings. And indeed, in this plot here on the bottom, they do show that this divergence feature is much higher for the unseen documents than the seen documents during pre-training. A black box technique that you can use, while white box with respect to the data, is just directly looking at the training data, such as in Elazar et al.'s What's in My Big Data. What they do is directly search and observe the model's outputs in the training data. It's possible that many of the seemingly emergent capabilities that LLMs have picked up are actually hidden in the training data. One compelling example that Yana and I found was by looking for let's think step by step in training corpora. There were tens of thousands of documents that were taken from a website that contains let's think by step as a way to provide answers in the C4 dataset. This presents a broader philosophical challenge for understanding how generalization works in the LLM era. Apologies for living near train tracks. Here are some examples of contamination from our own research. What we did was we looked at training sets for VLMs such as MS-COCO, Lion2B, Flickr30K, and others, and then we looked for examples from various test sets present in the training data. Indeed, we found that samples from datasets such as MMMU Pro contaminate some of these training resources considerably. We identify high and low risk level contamination samples. Sometimes the contamination just represents an image being present in both cases, but used in very different settings. For example, here we have an image that is identical and present in both MMMU and Lion2B. However, in MMMU, it has a common sense reasoning question, while in Lion2B it's instead accompanied with a caption. Now, of course, there probably are some connections between these two tasks where some generalization takes place. Perhaps a caption that documents that this image is an example of dredging and capping could lead the model to be better at answering that common sense reasoning question than it would otherwise be able to. Then there are also examples of contamination that are much potentially more harmful, but also different between the input and output, such as this image which gets cropped and zoomed in. Okay, so now I will be talking about the next class of issues, measurement issues. Measurement issues refer to challenges in benchmarking, which arise from, among other things, poorly developed rubrics and challenges with metrics that get used to grade or score the outputs of a model under test. If you'll permit me a small historical diversion, the term rubric comes from the Latin name for red ink writing, which in turn refers to the scoring guidelines that get used when writing assignments in the US education system. Traditionally, teachers would go through these homeworks with a red marker and mark the errors. Thus, the rubric pattern has grown popular in AI evaluation. In other words, the guidelines themselves that are used to do that red ink marking, both for guiding human annotators, usually non-expert crowd workers, in manually scoring outputs, and also for guiding LM judges in scoring the outputs. So how do we know when we're writing good rubrics, and does rubric quality matter? We care about the quality of rubrics, chiefly insofar as they impact the quality of judgments made by some judge. A popular type of judges for free-form outputs are LM judges, which have been present since at least 2021. With an LM judge, we prompt an LM to provide a numerical score given a set of requirements, such as truthfulness, informativeness, etc. This has some obvious advantages. You could specify your desiderata in natural language, which easily handles open-ended generations and gives some more interpretable results, and it can be quite straightforward to implement. However, there are some disadvantages too. These judges are brittle to variations in the input prompt. Implementing the rubric itself can be complicated, and there's also a documented effect of self-bias in LM judges. What is the problem with rubrics? Well, rubric quality matters a lot. So Sklar et al. Showed that LM judges can be extremely sensitive to minor variations in how the judge prompt is phrased. So how do we improve them? So how do we write good rubrics? In the work EvalGen, they point at a catch-22 in rubric writing, where in order to grade some outputs, you need criteria for good outputs. But to know the criteria for good outputs, you have to understand which errors occur, which can only be done through the process of grading. This is why educators often update the rubrics as they grade them. An observation from Shankar et al. 2024. In their work, they adopt a similar process for LM judges, where they take some seed rubric and first have a human review a set of outputs and grade them. After which an LM grades some of these sample outputs itself according to the rubric, and a human checks whether the assertions in the rubric which are given by the LM are in agreement with their own judgments or not, after which an LM can suggest where to edit the rubrics in order to improve it. This is one simple method that should be adopted during the benchmark development process in order to check that it actually measures what you want it to be measuring. Another problem that can arise, though, with rubrics is criteria drift. Static rubrics can be problematic because as models evolve and improve, the types of errors they make change. Rubrics which may be well suited to a poorly performing model may not apply as performant models have more nuanced weaknesses. In other words, not only do we have to update the samples as models get better, but we also have to update the rubrics themselves by which samples are judged. An example is this resource that I worked on with Feng et al. In 2024 that was targeted at 2023 to 2024 video generation models. In this work, we looked at problems such as temporal consistency, where some change to an object in the video over time is consistently represented by the model. Now, the models that we were evaluating at that time really struggled with this, but newer models like VO don't have this same problem. So, a big consideration that has to be made in producing a resource is the ways to make it more evergreen. Another issue with LM judges, beyond the question of how to write the best rubrics, is self-bias. Self-bias is the phenomenon where LM judges implicitly prefer text that's generated by their own base model. Xu et al. Demonstrated that across multiple models and multiple tasks, LM judges' self-bias grows as more refinement steps are made by the model. Here we have plots on the right for math reasoning and general text generation, which show that GPT-4, GPT-3.5, and Gemini all exhibit self-bias, which increases the more that each model revised the output answer. So LM judges really need to be carefully checked for these sorts of biases. These can lead to embarrassing failure modes, such as in the Exploring the MIT Mathematics and EECS curriculum paper. So in this paper, the authors claimed that GPT-4 can get nearly 100% on the core MIT EECS exams. However, a meta-evaluation showed many issues, including that with GPT-4 as the judge model, giving this inflated notion of the performance of the model itself on the tests. This led to the paper being withdrawn from the archive. Another class of measurement issues which are present are those with metrics themselves. So there are many other metrics which get used in evaluation that aren't strictly LM judge and rubrics. For example, in text-to-image evaluation, we want metrics for prompt consistency, the task of evaluating the extent to which a generated image aligns with the prompts that was used to generate it. There are multiple classes of prompt consistency metrics out there, which need to be compared head-to-head against each other. So two predominant classes of prompt consistency metrics are embedding correlation metrics and VLM VQA metrics. So what are these? Embedding correlation metrics, such as clip score, first embed the image and the prompt with clip, or some other embedding model that uses a joint multimodal embedding space, and then return the cosine similarity of the embeddings of each as the numerical score. Advantages of this method includes that they're cheap and fast, but there are some disadvantages too. The scores aren't directly attributable to any error in the image, and by the community they're generally considered less performant than other options. For VLM question answering metrics, we have an example in TIFA from Hu et al. 2023. TIFA uses a language model to first generate a list of requirements by reading just the prompt alone. Then it checks if each requirement is met in the image using a vision language model. This method is much more expensive than embedding correlation, but the scores are attributable directly to natural language requirements, and they were broadly considered more performant. However, in this task, there was an issue of flawed meta-evaluation. The superiority of the VLM VQA methods was assumed based on the correlation to human judges over unrelated images. However, this is an inherently subjective task. The way this evaluation would work is that we'd take some pair of unrelated image prompt pairs and then have a panel of human annotators assign their scores to each. These scores get averaged to provide some score for the image. If you're paying attention, this ties back into the averaging and subjectivity issue that we discussed in the data issues part. Then, two models under test would provide their own scores to those images. And whichever model reflects the judgments of the human annotators is said to be better. In this case, TIFA is performing better than ClipScore over these two unrelated image comparisons. In other words, we're checking how well the model is aligned to the average Likert scores that humans independently assign to image prompt pairs. However, this is inherently subjective. So we wanted to set out and test a more objective setting of this same problem. So what we did in our 2024 NeurIPS work, T2I Score, is we introduced semantic error graphs to evaluate these text-to-image metrics. Each graph contains populations of related images, which get organized by a counterfactual error count relative to the prompt. Then performance is instead judged by how well LMs reconstruct this error graph by ordering the images. This has the advantage that we don't have to worry about subjectivity in the severity of errors. We only need to check whether an image that contains strictly more errors by a basic counterfactual count is scored lower or higher than an image that is its parent on this tree. Here's an example where we have the error graph for a teddy bear underneath a Christmas tree covered in lights. We have these nodes 0, 1b, and 2, which contain different counts of errors. In this case, the teddy bear is missing from node 1b, and the lights and teddy bear are missing from node 2. We can look at the scores assigned by TIFA and ClipScore, and then look for their Spearman rank order correlation between the error count and the score that's assigned. When we do this, we can compare the embedding correlation metrics here in yellow with the VLM question answering metrics in blue. And we find that the seemingly dominant versions of TIFA, which are shown on the left with their scores that are tested based on pairwise unrelated preference correlation, collapse when we could instead consider their ability to order related images along these graphs. Once we performed a more ecologically valid meta-evaluation, the apparent superiority of some metrics over others collapses. This points to the fact that it's very important to meta-evaluate your metrics in addition to your samples to find ecological validity. So now I'm going to discuss the third class of issues in benchmarking, systemic issues. Systemic issues are cases where the manner in which an evaluation is conducted or made are problematic in and of themselves. One example that we'll discuss is the leaderboard illusion, where multiple submissions that are being made by the same provider can be used to effectively game leaderboard-style benchmarks, like Chatbot Arena. Then we'll discuss how illusory improvements in performance come from evaluating our models against weak baselines. We'll talk about how misreported variance by choosing best of n results skew the apparent performance of models. And all of these problems get sort of driven by this common canard of a problem, Goodhart's law, which is that once a measure becomes a target, it ceases to be a good measure. So first, let's discuss this leaderboard illusion. In Singh et al.'s 2025 work on the leaderboard illusion, they claim that rankings on these leaderboards get distorted. This is driven in part by Goodhart's law, because firms are increasingly using these arena scores to market how their model, such as Gemini, is better than some other model like Grok. There are four big classes of mechanisms by which firms intentionally or unintentionally cheat on these leaderboards. The first is data access disparity, where some providers get more chances to submit than others. This in turn leads to overfitting. Small amounts of data which are gained by doing these multiple submissions allow them to effectively game the arena. Then we have the ability of these providers to handpick scores, where undisclosed private testing allows them to only disclose the best score that they get. And finally, by being able to remove some models, it makes the performance look a little bit better for some than others. In turn, this drives the leaderboard illusion. How do they support this claim? Well, one compelling thing I saw in their work is this graph showing the correlation between the maximum ARENA score that some provider or producer gets and the total number of models that they submit at once. It seems that there's a pretty clear hill climbing effect going on here, where OpenAI and Google get so many shots to test so many different models that they're effectively able to get a much higher ELO. What's wrong with making multiple attempts in general? Well, when you get to report an asymmetrical number of best of n runs on one class than another, this leads to a big statistical problem. Yanni and Mimno's 2024 column paper on getting better random baselines for evaluation of prompt sampling was a really compelling example to me. So what they show in this work is that taking the best of n for one model but not the other leads to a distorting effect. So here on the top we see the number of different prompts that can be provided for an input system and their overall performance in classifying some task. What happens in most of these papers is that we try a bunch of different classifiers and then report the best performing one as the system in itself. Then we compare it against a baseline, which is the expectation over random classifiers. When we talk about the expectation of random, what we mean really is sampling from some number of classifiers, which provide some random output label to each, and take the expectation over those, which will give us the middle of this normal distribution of possible scores. However, some random classifiers are going to get really lucky. There's an infinitesimal chance that you may even correctly guess all the labels. So really what you need to do when you do a best of n sample is actually take samples of n of these random classifiers and similarly take the best performing ones. That yields this lopsided distribution of best of n for many of these random samples of classifiers, and this can sometimes lead to an actual higher maximum expected random accuracy than the base accuracy across different tested systems. So it's even possible for this leaderboard multi-submission gaming attempt to cause random classifiers to outperform good ones. So what can we expect to see when model providers are submitting multiple good system runs? This helps drive the leaderboard illusion, when we're doing this not on random baselines, but instead against competing models. Another systemic issue is the way that variance is reported, and this is related to the previous two problems. So Rule et al. Discuss how intramodel variance in statistical reporting leads to some noise problems. So by reporting a single number for some new method or model, rather than the results according to multiple seeds, temperatures, and etc., makes it very difficult to distinguish the signal in the improvement of performance from the noise. So the wider that the intramodel variance is for some submitted number of runs, the lower resolution a benchmark is going to be. This causes rankings to become unreliable. Unfortunately, it's really expensive to ask all the providers to do several extra training runs just for the purpose of distinguishing this signal from noise. But if we can't, what are we doing? The final class of issues that I will be discussing are the most abstract, epistemic issues. Epistemic issues represent core failures of conceptualization and operationalization in benchmarking, which cut across all of the more concrete issues we discussed before. So what we're going to discuss here is how tasks and learning problems need to be separated in our conceptualization, and how the conflation of two within a task universe causes problems. We'll talk about confusions of map and territory when thinking about AI. And we'll talk about the pitfalls of treating benchmarks like psychometrics for humans. First, I'll discuss an important distinction from Joao et al. The distinction between tasks and learning problems. Tasks are often conceptualized at different scales within a task universe, shown here on the left in this illustration. One researcher may think of themselves as working specifically on X-ray detection of pneumonia, while another might consider themselves working specifically on medical image classification. Another may think about classification, while some think about computer vision in general. As we try to produce foundation models, they represent attempts to make systems that can perform tasks at higher and higher levels within this universe. However, learning problems, in other words, the datasets themselves, are distinct from tasks. ImageNet is a learning problem, which is purported to capture the task of natural image classification. However, it is the map and not the territory of image classification. When we talk about problems of map and territory, one issue is wishful mnemonics. Melanie Mitchell presented some fallacies in her 2021 work about AI thought, which are hampering our progress towards AGI. Wishful mnemonics are one. They're a critical fallacy, which chronically plagues benchmarkers, by which our thinking about what a learning problem is are shaped by what we call them as a task. When we call some part of a program reasoning or understanding, we're effectively assigning our understanding of what understanding is onto the system itself. So when we do this, we're begging the question that a model's performance on some tasks represents an abstract capability. But does it? Chronic failures of models to generalize across different reasoning tasks suggest that the answer is no. Coupled with the sloppy application of learning problems to these tasks, we're often seriously considering the map, in other words, the scores on benchmarks, with the territory of overall performance. The biggest map territory issue, as far as I see it, is the trap of looking for generalized psychometrics for AI systems. So when we give standardized tests to humans, we have a shared architecture between each other that we can use to reason about their performance. We know that a lawyer who can pass the bar can also be a good lawyer because the process by which a human prepares to pass the bar, in other words, studying a considerable corpus of legal cases, is the same fundamental skill that a human uses to perform as a lawyer, as they have to be familiar with prior case law, at least in common law systems, and they also have to be capable of studying the particulars of the case. However, as we see a jagged frontier problem in the development of AI, we need to think twice about whether these psychometrics work. There are some competing visions between what this jagged frontier problem is. By the jagged frontier problem, I of course mean that for some tasks the AI can perform at a superhuman ability, while for other tasks it can perform, for some learning problems it can outperform humans, while for others it can't, even within the confines of what we consider to be the same task. And there are these competing visions, where one is that we're making our way towards the models eventually being able to outperform humans on all tasks along this jagged frontier, while another vision might be that some tasks are just fundamentally intractable for AIs. So let's conclude with a summary of what we just talked about. We talked a lot throughout data, measurement, and systemic issues about noise. Bad examples produce a noise ceiling and also a lower resolution throughout the entire performance range. Poor statistical systemic practices also lower the resolution through variance-based noise bands. And problems with metrics can also introduce noise. And resolving any of these issues may cause the ranking of systems to completely swap, challenging the validity of the benchmark themselves. Another theme that came up throughout this talk is the need for careful conceptualization. Construct validity is necessary, both for good data collection and for good metric design and validation. One big problem that we discussed in conceptualization is that of the distinction between tasks and learning problems, and how they confuse map for territory. We also talked a lot about the positionality of humans who are doing the work of benchmarking. Throughout the benchmarking process, we have humans doing work, and they bring positionality along with them, which often gets overlooked. Bad samples can come from exhausted crowd workers, or misinformed crowd workers, or from random people on the internet whose data we are non-consensually taking for evaluation. AI researchers often lack domain expertise to really understand the problems that they're trying to make systems for, and hidden cultural assumptions that are present and driving the decisions of annotators and producers also introduce positionality, which needs to be interrogated when we claim that some benchmark or resource is good. So there are some open questions that I want you to think about and take away from this talk. What counts as contamination when we're looking for systems that do everything? Does it count as generalization or not? When we need to train LMs on every single problem out there ostensibly to get them to perform well, and does it count as contamination when we do that? Do those weaknesses exist in LLMs and our way of thinking about them when they weren't present in specialized models? Are we producing intelligence at all if we have to explicitly train the model on every individual task? And what questions does that introduce for benchmarking? So some of these came up in our panel discussion, which has been posted to YouTube already. So thank you for watching this excerpt of the presentation. Throughout it, I've provided reference to a variety of different papers, which are all documented in our bibliography at benchmarking.science/bibliography. Thanks again for watching.